All cars have grilles located at the front of the vehicle. A grille has the important job of directing cool air into the radiator, which stops the engine from overheating.
The process works by pumping a coolant mixture through the engine into the radiator, which then cools the coolant before redistributing this back into the engine.
We hypothesise that high-performance cars will have the most effective grilles for heat transfer, and that low-performance cars will have the least effective. We propose to test 5 generic car grilles from different performance categories to observe the difference in heat transfer efficiency. We will begin by designing 5 grilles on Autodesk Fusion 360, all with the same 10mm border and all cut from a 155mm by 154mm test piece, which fits into the heat exchanger.
We will then power on the heat exchanger and take a baseline reading to see the temperature difference between the intake and outlet water. This is done in order to compare our grills to this reading. We will start from what we believe to be the lowest performance grill, Grill A, and work towards the highest performing grill, Grill E. From this information we'll be able to conclude which grill is the most efficient for heat transfer.
Here we're taking the baseline with no grill in the apparatus. Now we're putting the grill A in the machine, making sure not to trap any wires. After setting a timer for 3 minutes to allow the temperature gradient to form, we take the results and realise that there's no difference between the baseline and the grill. So we talk it over and decide to produce grill F to artificially create the temperature gradient and use a thermal imaging camera to see the results. After completing our experiment, we can conclude that our hypothesis was incorrect. In reality, the grill design in this experiment made no significant difference to the cooling of the water within the heat exchanger. We then manufactured a 6th grill, Grill F, with a 10x10mm square cut in one of the corners. We then inserted this into the heat exchanger and recorded the same data as the previous test. Additionally, we recorded extra data in the form of multiple infrared camera shots. This allowed us to see how the heat was dispersed inside the heat exchanger and highlighted that when using Grill F, the heat transfer was focused within a specific area around the square.
From the initial 5 grills, we observed little to no deviation from the baseline results. We believe this is due to all of the grills being similarly uniform and symmetrical by design. In our opinion, this infers approximately the same volume of air is able to flow past each grill, therefore cooling the water inside the heat exchanger to around the same temperature. However, Grill F yielded a varying temperature change of 0.7 instead of 2.2 due to its design restricting the volume of air to pass through the heat exchanger.
When we looked over the grill F using the thermal imaging camera, the unobstructed corner showed the highest heat transfer, whereas the obstructed area showed a considerably higher temperature. We can use this information to conclude, given a suitable area and a uniform design, any grill can produce an effective heat exchange to stop cooling from being the limiting factor in an engine's capability.